Okay, so I hope it's all right. So I'm recording now. I mean, and probably, yeah, valuable time is lost anyway. So
Sorry, if you click on save, it will give you the option of this and all following events.
no, it's not. It
I
just
think you need to make some change, sir. If you don't make any change,
So
it won't
there's
give
one
you
thing
save
like
option.
title or something.
yeah, just I mean, yes. Okay, then on
So it will
yeah,
give
but
the
That's all
option on
fine.
saving.
this and the following events. Okay, all right.
Yes, sir.
Okay, okay. I hope this settles it. So that means the link address is different now. I need to update the classwork folder also, right? Because the classwork has the old folder, I mean old link. So let me do that before I forget. Think.
So the meet link is the same for the updated event.
Okay, hopefully. But anyway, I just posted on the. Okay, yeah. So anyway, fine. Let's get going. Okay, and before I forget, let me tell you that I have posted an assignment on the classwork folder. Okay, and I think it's due on September 2nd. It's just one problem. So
Sir,
you can
we are
see
not added on Classroom, so we cannot see the assignments.
everybody is added to Classroom, right? I mean the
Sir,
folder because.
after ad swap, the people have not been updated.
So so you just send me one email. Okay, so I'll just add you to the classwork folder.
Okay, sure, thank you, sir.
Okay. Anyway, so I'll just show you the assignment then for now, so that so this is just one problem that in the classwork folder. It's just yeah. So can you see this? Can you see the assignment?
Yes, sir.
Yes, sir.
Okay. All right then. Fine. So you can just take a note. I mean, those who don't have access to the classwork folder yet, you can just take a note, right? And then it's a very simple problem. I mean, you just have to think a little bit, right? I mean, it's sort of out of the box. So you have a set of linearly independent vectors in one vector space V, right? Okay, and then you have another vector in that same vector space. Okay, so what you are going to do now, you just add that vector to each one of the vectors in the list. Which list? The linearly independent list. And so you get a new list, right? Okay. So what you have to prove is that the new list, which is V1 plus W, V2 plus W, all the way up to Vn plus W, if this new list is a linearly dependent list, then that means W is already in the span of the vectors V1 through Vn. Okay, so this is what you got to show. Okay, so what this means is what you have to show is that any vector in the span of a set of vectors, meaning what? You can express that vector W as a linear combination of V1 through Vn. That's all you have to show. See, in order, so an equivalent statement is you need to show that W is equal to, let's say, B1 V1 plus B2 V2 all the way up to Bn Vn. This is what you need to show. Okay, all right, using the concept of linearly independent set, which is already a spanning list in the vector space V. Okay, all right, and there are constants associated with V1 through Vn such that the linear combination of V1 through Vn, if you set it equal to 0, those constants are identically 0. This is the definition of linear independence. Okay, all right, so I have already given you 40% of the solution. Okay, you just have to fill in the blanks. It's just one problem. Okay, so where were we? We were talking about vector spaces, right? Okay, so there are a bunch of properties. You know, the last property number 10 is actually a typo. So you'll just, you know, it's just 1 times u is should be equal to u. Ignore that z. It's just a typo. Okay, so there are a bunch of properties. I mean, so what you can see right here is that, you know, some of the things that you would commonly assume works. But I mean, those things work for numbers only, scalars only, right? I mean, in your vector space, typically your elements are column vectors or even matrices, right? So some of the things which naturally work for numbers may not work for these guys, okay? So you have this commutative rule for addition, okay? So you are defining 2 operations here. One is the addition operation and the other one is the multiplication operation. So when you're defining the addition operation, I mean, you are saying that the addition is commutative, right? It's also associative, which means you can put brackets when you are adding, you can put parentheses wherever you want, it doesn't matter. Okay, and then if you're adding, then there is an identity element should be in your vector space. Now, in terms of, if you think of matrices, this is just the 0 matrix, right? You have a 2 by 2 matrix, right? 2 by 2 non-zero matrix, and then you have a 2 by 2 zero matrix. So when you add that 2 by 2 zero matrix to that non-zero matrix, you get back the non-zero matrix, right? Nothing changes. And you do that from either side, left or the right, doesn't matter. Okay, so this is called the identity element with respect to addition. Okay, all right. And since you have an identity element with respect to addition, for every element in the vector space, you also have its, you know, reciprocal, or not exactly, I should not be saying the word reciprocal, you should be having its inverse element, okay, which is nothing but negative of that. This is with respect to addition only, so that when you add the element u and minus u, you recover the identity element. Okay, as simple as that. Okay, so you multiply a matrix with another, sorry, you add a matrix with another matrix where each element of the matrix is exactly the negative of the elements in the original matrix or the other matrix. When you add these 2 up, you're going to get a 0 matrix. Okay, and then you have closure with respect to scalar multiplication, right? And then what happens is that scalar multiplication is also associative. Okay, all right. It is also it is so this is with respect to scalar multiplication. And then if you have defined a multiplication operator, then you take an element and you multiply that with an identity. Okay, you should get back that element. So in terms of matrix multiplication, what it means, I mean, in terms of linear transformations on which induces a matrix, what it means that you take a matrix, you multiply it with its identity matrix, right? Okay, you should recover the original matrix. All right, so bunch of properties. The question is, if I ask you or anyone asks you, okay, I give you an example of a vector space, I mean, I give you an example, show that it's a vector space, right? Okay, then you have to actually physically go through verifying all these 10 properties, which is a pain, right? I mean, there is an example, right? I mean, it's an easy process. It's an easy enough process, but it's painful. Okay, all right. I'm never going to ask you to do that. I mean, neither in test or whatever. Okay, I will not. But I mean, it is imperative that you know how to do it. Okay, so in this particular vector space, if I define an algebraic operation this way, right, and algebraic operations are defined, right, in customized manner, then can you show that this is a vector space as well under this particular algebraic operation or linear transformation? Okay, so you take 2 vectors. I mean, you have to basically verify all of these properties one by one. Okay, all right. I'm going to skip through this because I mean it's really an algebraic operation, nothing more, nothing less, right? But you have to carefully show each and every property. Okay, all right. So you start with, you know, a closure, right, and then commutativity, associativity, right, and then the inverse with respect to addition, and then identity element with respect to addition, inverse with scalar multiplication, and everything. And in this particular case, it turns out that the scalar multiplication does not distribute. Okay, it does not follow the distributive property, and therefore it's not a vector space. Okay, so as I said, a vector space is a set. It has to have the properties of a straight, a closed structure, sort of a kind of a thing, right? I mean, but it is much more than a set. Okay, all right. Now, what is more interesting to figure out is that given a vector space, I mean, is there a way to figure out? Is there a way to figure out whether if you take a small slice of a vector space, okay, whether that slice itself is a vector space or not? Okay, it turns out if that slice itself is a vector space, okay, then it's a subspace. It's called a subspace of the original vector space. Not every subset. So basically what you are doing is you are taking subset of vector spaces, but not every subset of a vector space turns out to be a vector space itself. Okay, so there are now generally by brute force, what does it mean? You already have like 10 properties of vector spaces, right? You have 10 properties, right? And I give you a subset of that vector space. And what I'm asking is, show me that this subset is also a vector space. What are your options? Your option is just to verify all the 10 properties, whether all those 10 properties work for that subsets as well, right? That's a really painful option. And then there is a slick option, a beautiful concept called subspace, where you really don't have to verify all the 10 properties. Because remember, a subspace also has to be a vector space. But in lieu of verifying all the 10 properties, you are just verifying 2 properties. Just 2, imagine. And what are those 2? It says that if I have, so let me just now go to the whiteboard, right? So what it says is, I have sort of a vector space V, okay? And then what I do is, I sort of chop off this portion, right? And this is a subset of the vector space. This is the W. W is a subset of V. Okay, all right. W is a subset of V. So what I need to do is, what I need to show is that W is a subspace of V. What this implies is the following, that let's say you take 2 elements in W, right? So let's say 2 elements in W, A and B. Okay. Now, if these 2 elements A and B belong to W, that means that these guys will belong to the vector space V as well, right? Okay, because V is the superset, all right? But as I said, instead of, rather, sorry, let me choose this one. So instead of the 10 properties, I just need 2, which is A, B in W. Does it imply that A plus B is also in W? Number 2, A in W, and you choose a scalar from the set of real numbers. And does it imply that this is in Okay, if these two properties are satisfied, then that's it. You really don't have to verify all the 10 properties. So my question is the following. My question is the following, is that why? Why are these two properties sufficient? Anyone? Why are these two properties sufficient? Hmm?
Because if A and B are elements of W, then they have to be elements of the original vector space. Then
Right.
they
So
will
see
satisfy all the
yeah.
properties of that vector
Correct.
space,
Correct.
which we know is a vector space. V is a vector space.
Correct. So what happens is the following, that the other 8 properties. Now the first thing is that W is a subset of V, right? So by virtue of W being a subset of V and V being a subspace, right? The other properties such as distribution, associativity, additive inverse, multiplicative inverse, all these are properties of a vector space V which are inherited to the subset. Okay, so you really don't need to care about the other 8 properties. So these two would be good enough. Okay, so now, then the question is, there is another question that I need to ask, is that, why do we care about subspaces? Why subspaces? Starting from signal processing to machine learning, this is a direct implication. This is a direct implication, right? And these are basically, if you want to project your learning space onto lower rank subspaces where you can actually segregate one particular feature from another feature to look at each and every feature. So then this kind of subspace decomposition is very, very useful. So from an abstract point of view, what I mean is the following, is that let's say I have a vector space V, and then I have two subspaces, W1 and W2. Okay, all right. Both of these are subspaces of the vector space. Okay. Now, are these W1 and W2 some special subspace such that when I add the two subspaces, I get back V in full, okay, in such a way that there is no intersection between the subspaces W1 and W2. Say something like this. Sort of like this. You have W1 here and W2 here. Okay, all right. So is there, so W1 is a subspace of V. W2 is also a subspace of V. And V is an algebraic sum of W1 plus W2 as a set, and W1 intersection W2 is null. Okay, if that happens, then you can uniquely decompose V in the following manner. And this kind of decomposition is known as a direct sum decomposition of vector spaces. Okay, all that is, jolly good. But once again, you might ask, where is this direct sum decomposition of vector spaces useful? Where do we actually use it? Okay, So in order to answer that question, we have to, you are familiar with orthogonality a little bit, right? We spoke about inner products, we spoke about vectors which are orthogonal to each other. Now let's talk about, vector spaces which are actually orthogonal to each other. Okay, so I think, I mean, a lot of you are familiar with support vector machine. You have already, you studied support vector machines, right? I mean, some of you studied support vector machines, right? Okay, I don't know in how much detail, but at least what I anticipate is that, I mean, Professor Ashwin will do a very good job in talking about the details of support vector machines, right? Okay, so roughly, a support vector machine works like this, that there is generally a margin that is being created between two classes of objects, right? A margin as large as possible, such that you will have objects belonging to, you'll have objects belonging to two classes which are separated by this large margin, right? Okay, and so that these guys, which is class 2, do not fall, close enough to class 1. Okay, now the question is, it's easy to say such things, right? But how do we actually accomplish it? Now, to begin with, I mean, there is no requirement that all of these training data points, which are just column vectors, right? Because you store the features here, all of these training data points are orthogonal to each other. There is no such requirement, right? But assume that there is one guy which falls here. Okay, all right, misclassified. What am I going to do about it? So the best way is to project this guy onto the other side of the width where it should belong, right? But how am I going to project this? Okay, now what happens is, what you can do is, I mean, you can go in some direction over here, right? And then you can go in some direction over here, because you have to cross this margin, right? Okay, but as I said, I mean, you can also have a projection, an orthogonal projection, because that seems to be the shortest distance. Okay, so you basically have to use inner products, a bunch of inner products. Okay, all right, and you orthogonally project this data point onto the other side. So when you are done classifying with 100% accuracy, right? I mean, you would expect that your class 1 vectors and class 2 vectors are segregated by a large margin in such a way that, I mean, any vector on the other side of the margin is actually an orthogonal projection of vectors from this side. Okay, so I mean, we can think of this. We can think of this as, W1. Let's say a special kind of W1. We can think of this as W2, and then what really happens is, see, these two guys, W1 and W2, are subspaces of vector spaces, and therefore they're vector spaces in their own rights. And since you have separated W1 and W2 by a large margin, there is no way, I mean, theoretically speaking, there should be the intersection between W1 and W2 should be null, correct? Okay, all right. And what you can say is, these subspace itself, W1 and W2, are orthogonal to each other in the sense that elements in W1 are perpendicular to elements in W2. Okay, and so therefore, what you can do is, you can write a vector space as a direct sum of W1 and W2. Now, what I want to do is that I want to replace this W1, just rewrite this W1. Okay, all right. I want to rewrite this W1, and I want to introduce W1 direct sum W1. This is your high school representation of orthogonality, right? Perpendicular. So this W1 star, this W1, whatever this notation you call, this is nothing but an orthogonal complement of W1. Okay, in such a way that sometimes your ortho is in such a way that there is no intersection between W1 and its orthogonal complement. Okay, so each one of them, W1 and W1 complement, right, are vector spaces in their own right, and they are subspaces of V. Okay, and this kind of special arrangement or special kind of direct sum decomposition is useful in interpreting how a support vector machine works. A linear classifier, that is, I mean, not a non-linear one. I'm just talking about a linear classifier. Okay, all right. So therefore, so let's have a checklist or a couple of things, you know, our way. Okay, which is, I mean, we have a formal notion of a vector space now, right? We have a formal notion of a vector space, right? And subspace, right? Complement of a vector space, right? So generally complement of a vector space is another vector space, right, where the elements of this particular vector space will not be found. Okay, so complement of a vector space, and then orthogonal complement and direct sum. Okay, this is, and as I said, a case study, the support vector machine is a classic case study in this. Okay, all right. Okay, now so you understood the concept of subspaces, right? And you understood where this is used. So let's look at some examples. I mean, every vector space is actually a subspace of itself, but that such kind of subspaces are called improper subspaces. Similarly, the zero vector space, I mean, vector space containing the zero element only, is also a subspace of the vector space V. Okay, so some like R3, if you take the example of R3, which is, you know, three-dimensional real space, right? These subspaces are the zero vector, right? I mean, plane through the origin, etc. Okay, all right. And so zero vector and the R3 are actually improper subspaces of R3. Lines to the origin, planes to the origin, like 2x plus 3y equal to 7, that is a subspace of R3. Okay, all right. So interestingly enough, if I have a bunch of subspaces of a vector space, then the intersection of the bunch of subspaces is also a vector space. And this is really easy to show by using the same properties of subspaces. Okay, all right. So like now, this is something that you probably are not familiar with. Let me take an example of, you know, W be a set of all 2x2 symmetric matrices. You know what a symmetric matrix is, or a corresponding linear transformation, correct? Okay, so this W should be a subspace of the vector spaces of all 2x2 matrices, where you have defined standard addition and scalar multiplication. Simple enough, right? So you take any two such, you know, matrices from that space W, and those will be 2x2 matrices, right? And you know that each one of them will be real and symmetric, which means A1 transpose is A1, A2 transpose is A2. Now, what are the properties of subspaces? You got to show two properties, right? Is that its closure with respect to scalar addition and closure with respect to scalar multiplication, right? So you take A1 and A2, both from the vector space W, right? And you first look at what is A1 plus A2 whole to the transpose. Well, we know from the properties of transpose, right? It's no big deal that A1 plus A2 transpose is A1 transpose plus A2 transpose. And since A1 and A2 are real and symmetric, you can replace A1 transpose and A2 transpose with A1 plus A2. So in general, okay, so therefore your A1 plus A2 is closed in W, right? Okay, all right. And the scalar multiplication, you just take the matrix, multiply with under the operation of the transpose, right? But you once again know that A transpose is A, and since K is a scalar, the transpose operation will have no effect of it. So for every vector or every element A in W, Ka belongs to W as well. And so therefore, this particular set of all 2 by 2 real symmetric matrices is actually a vector space itself and a subspace of a general vector space of 2 by 2 matrices. Okay. Span, we already know this, right? I'm not going to talk about this. I mean, there's only one thing that I would like to mention is that if you are asked how check that whether this particular vector is in the span of some vector space, right? So what you have to do is that you have to know the basis of that vector space. So in this particular case, your vector space is V, right? So imagine there exists a basis of this vector space V1 through Vn, right? And if you are checking whether an arbitrary vector small b is in the span of this vector space, all you have to do is to be able to represent this arbitrary vector b as a linear combination of those bases. So you write it, and then it gives you a system of equations, right? Okay, it gives you a system of equations. All you have to check is that whether this system of equation is consistent or not. What does it mean? Consistency of a system of equation implies that whether you have a full rank matrix. Okay, all right. So, I mean, this is something that we will talk about later because I haven't yet introduced row rank, column rank, rank nullity theorem, and things like that. But this is one way of checking. And the way he has done it is basically he wants to compute the inverse of that matrix eventually and see if the inverse exists, that the system is consistent. As I told you, I will not adopt that particular approach. I don't like computing inverses of matrices, and I think you should also avoid doing such a thing, right? So we will look at it from a different perspective. The logic is same. If the inverse of a linear transformation exists, all you have to show that the linear transformation is a bijective one. Okay, and if the linear transformation is a bijective one, then that vector, arbitrary vector b, is in the span of that vector space. Okay, we have talked about this anyway, but I have shared the slides with you in the classwork folder. So this is linear combination and examples of linear combination and so on and so forth. Okay, all right. So I mean, these are, I'm going to skip this because we really have spoken about all of this. Okay. By the way, what I mean, as I said, I'll just repeat for those who join later. I mean, we are following Sheldon Exler's Linear Algebra Done Right textbook, and that book is uploaded. A soft copy of that book is uploaded in the classwork folder, right? And by the time we arrive at the first internal, I mean first test or whatever, okay, I mean we would be covering approximately 1.5 chapters. So chapter 1 of Sheldon Exler and about 70% of chapter 2. Okay, this will be the content of the first test. I mean, I probably am stretching it a bit far. I may not be able to get to that 70% of chapter 2, but at least 1.5. Okay, all right. Okay, so all of this we have already covered, so there is no need to actually talk about all of that, right? Linear independence and stuff like that. Okay, so I mean, so now I think what we should do is talk about come back to basis, because we've been speaking about vector spaces, right? So we come back to basis, right? Okay. So now we know that a basis of a vector space is an important concept, right? Because it is directly tied to the dimension of the vector space itself. Okay. Now, what is this? This is nothing but an orthonormal basis. Okay. All right. Now, this is particularly important Because where have you seen an orthonormal basis, guys? Have you seen orthonormal basis before? I mean, at least in my class lecture, there is a passing reference. Have you heard of, I mean, have you seen orthonormal basis? You definitely have heard of it. Have you seen orthonormal basis? You sure have. I mean, when we are discussing principal component analysis, unit vectors are orthonormal. Yes, excellent, excellent. But I mean, other than that, other than the almost trivial examples, right? I mean, one good example that you have seen connecting to a real world application is in PCA, where, if you recall, we had a real symmetric linear transformation, right? And then the corresponding eigenvalues were real and distinct. And therefore, what you have done, what we were able to do, is to decompose the original vector into a set of other, decompose the original matrix, which is a correlation matrix, into a set of other matrices, right? And in such a way that the new matrices are actually formed out of orthonormal basis. Okay, so let me tell you what I mean by this. What I mean by it is the following: that if there are some spatial matrix, okay, if A is real and symmetric, then A can be written in this manner. Okay, where D is nothing but a diagonal matrix. Okay, you know that diagonal matrices or diagonal linear transformations are nice, right? Because it's really easy to compute the inverse, transpose, whatever. Okay, now we were talking about orthonormality. We know that, I mean, in general, you know that a matrix induced by a linear transformation satisfies this property, right? So that it is orthogonal, correct? Right? Now, what is orthonormal? An orthonormal has to be orthogonal plus the length of the vectors has to be equal to 1. The norm of the vectors has to be equal to 1. And you know that norm is induced by inner products, right? Okay. So when we talk about orthonormal basis, we actually talk about inner products, right? Inner products, and we actually talk about orthonormal linear transformations and their properties. Okay, so let's talk about this first. Okay, now what it says is that if your linear transformation is real and symmetric, you can actually break it up, and I mean, of course it has to be square. Okay, you actually can break it up into 3 parts. This part is done, understood. What is P? This P is nothing but it is actually another linear transformation on matrix corresponding to the eigenvectors of the matrix A. Okay. Now, if you already know that if there is a matrix that is real and symmetric and its eigenvalues are real and unequal, distinct, right? Then the corresponding eigenvectors are actually, orthogonal to each other. We have already proved it, right? And so that basically gives us this matrix. And if it's really orthogonal, right? And we can also actually show that orthonormality or orthogonality also gives rise to linear independence, right? So what happens is you have a set of columns in your matrix which are linearly independent. Okay, and therefore you have a full rank of this matrix. And if you have a full rank matrix, its inverse is also well defined. So you will be able to express this matrix A, decompose it into 3 parts. Now, what's so nice about being able to decompose this into two parts? Because you really don't have to deal with this, whatever this next nasty matrix is. You're actually now dealing with a much nicer matrices. Okay, all right, or linear transformations. Moreover, there is another practical, very sweet application. And I mean, the point is, I mean, for notorious computations, such kind of decompositions really help. Like, for example, if I want to, exponentiate this matrix raised to the power n, and this arbitrary n is like, it could be a million, it could be a billion, or whatever, right? So in essence, if the matrix A is real and symmetric, by matrix I mean the linear transformation, okay, is real and symmetric, then what you have here is that this guy PDP inverse multiplied with itself n number of times, isn't it? Okay, and so therefore, I mean, what you can see is that there are collapsing matrices in between, except the matrix on your leftmost matrix, and except this guy, everything else will collapse. Okay, and then your D's will remain. So how many D's will remain? So you see how nice this has turned out to be. Okay, so if your matrix or a linear transformation is real and symmetric, you actually have this result. Okay, and on top of that, if your transformation is orthogonal, then you have a further nice decomposition, which is you can write A as P, D, and since P is orthogonal, right? Okay, you can replace P inverse with P transpose. And this is known as orthogonal decomposition of real symmetric matrices. An extension of this is directly used in singular value decomposition, where your original matrix to begin with is no longer a square one. Okay, you can still actually extend this out. Okay, all right. So, I mean, I think we have set up the platform for the next lecture where we will extend this out. Okay, this orthogonality, talk about some properties of orthogonal linear transformation, and from there I will come back to what I promised in the first class, is that I will show you that if a set of vectors is orthogonal to each other, then they are also linearly independent. Okay, which is a property of the set of eigenvectors which we wanted to establish to begin with. I would also want to then go back to the characteristic equation that you are so proficient in solving and finding out the eigenvalues and eigenvectors, and question the validity of that equation itself. This is what we must discuss in the next class. I mean, what does it really mean when you say that, determinant of A minus lambda I n gives us the eigenvalues? In other words, what is the real meaning of A minus lambda I equal to 0? Okay, but before that, we need to talk about the rank of a linear transformation, nullity of a linear transformation, and so on. Okay, all right. The name of the book is Sheldon Axler. It's already uploaded. The textbook is uploaded in the classwork folder. Okay. Yeah. It's already.
Sir, so basically, if
Yeah.
Sir, so if the inner product of two vectors is